Hi, well, we're going to spend pretty much almost the rest of this entire unit talking about two very common reactions that organohalides will undergo. And these two types are called substitution and elimination. Um, Sorry, my computer's bugging up. Substitution and elimination, depending on what the end result is. So in a substitution, a halogen gets replaced by a nucleophile. And in an elimination, a base is used to pull off a hydrogen, form a pi bond, and kick off a halogen. In each case, the halide is acting as a leaving group. We've talked a little bit about leaving groups before. I'll go talk a little bit about them again shortly. But the reason we talk about these two reactions together is that they are often in competition with each other. I kind of refer to this as like the World Series of OCHEM, um, because some nucleophiles are also bases. And so there's this competition between, does the nucleophile want to be a nucleophile and do a substitution, or does the nucleophile want to be a base and do an elimination? So let's just kind of, quick comparison here. Let's say we do this reaction, and here we have hydroxide. Hydroxide's a good nucleophile, but it's also a really strong base. And so what we find is that we do get a couple of products. We get the substitution product, which in this case is the major product. Most of it is the substitution product, but we will find a very small amount of the elimination product. That's the very minor product. Now, if I take the same nucleophile and react it with this alkyl halide, we say there's a different story. Now we have a mixture of the two. And it's not like it's an equal mixture, but it's more than, oh, a vast majority of substitution or elimination. So depending on the reaction, it could be, I don't know, 70-30, 80-20, 60-40. It's just that there's a significant amount more of elimination. And then finally, if we just change this alkyl halide one more time, in this case, for this reaction, the only product obtained is the elimination product. So what we're going to be able to do by the time we end this unit is be able to look at a reaction and determine whether this is going to be predominantly substitution or elimination or a mixture of both. Now, because this deals with halides acting as leaving groups, I do want to review this as something that I talked about previously. So I highly recommend reviewing it. Halides are ideal for these kinds of reactions. Number one, due to the difference in electronegativity with carbon, and they are stable once they leave. So if we look at a carbon halogen bond, since the halides are more electronegative than carbon, that creates a partial positive region on the carbon, which a nucleophile would love to make a bond with. And halides, once they leave, they form that X minus, which is a stable ion. Now, it's very important to know what's stable when it leaves, what's not stable once it leaves. And there, as I spoke about earlier, there's a direct relationship between the type of base that anion is once it leaves and how good of a leaving group is. So the best leaving groups are the conjugate bases of a strong acid. So remember back in our acid base unit, the stronger the acid, the more stable the base it produces, or I should say more stable conjugate base it produces when that proton transfer occurs. And if the conjugate base is stronger, like in the case of these down here, those are not going to be great leaving groups. So that's just a little bit of a review about why most of the halides, chlorine, bromine, iodine, are really good leaving groups. So let's talk a little bit about substitution. In a substitution reaction, two things happen. A leaving group leaves, and a nucleophile takes its place. Now, the order of those two things depends on which mechanism the reaction decides to go through. Within nucleophilic substitution, there are two competing mechanisms. The first of these we call SN2. Now, the S in that term means substitution. The N, which we kind of write as like a subscript, the N refers to nucleophilic. And then two is just not kind of a placeholder. It actually means something. The two means that the reaction is bimolecular, meaning that in the rate determining step of the mechanism, there are two chemical species involved. And so the rate law for an SN2 mechanism is equal to K, the rate constant, don't worry about having to calculate that, times the concentration of the alkyl halide times the concentration of the nucleophile. Notice in this rate law, which is a measure of the rate determining step, it's dependent upon both reactants. If you change one, you change the rate of the reaction. If you change the other, the rate of the reaction changes as well. Now you might hear me refer to this as also the substrate. So I'll use those terms interchangeably. It's just most of the time we're going to be dealing with alkyl halides. And the mechanism for an SN2 is what we call concerted, meaning it happens all at once. Everything happens in the same step. Now, just to kind of draw out a generic mechanism of an SN2, we'll have a nucleophile and then our alkyl halide. Since both of them are involved in the rate determining step, the mechanism is going to demonstrate that as the nucleophile comes in, it makes a bond with the carbon with the leaving group. That's the X there. And the leaving group leaves. So we're drawing an arrow to show a bond forming between the nucleophile and the carbon, and an arrow showing the bond breaking between the carbon and the halogen. And so now the nucleophile used to be where the halogen was, and the halide's just kind of floating around. Now this mechanism is in competition with what's known as SN1. Again, the S and the N mean the same thing. S means substitution, N means nucleophilic. The 1 means that this is a unimolecular mechanism, meaning that the rate determining step is dependent upon one chemical species. In this case, it is dependent upon the concentration of the alkyl halide. So it's important to note the nucleophile is not involved in the rate determining step. And scientists discovered these two competing mechanisms. One of the ways through which they discovered it is doing kinetic experiments. They found that certain substitution reactions, the rate depended on the concentration of both the nucleophile and the alkyl halide. And then in certain other reactions, they found the rate of the substitution depended only on the alkyl halide. And they came to the conclusion, well, there has to be two different mechanisms if that's the case. If in some, the rate's dependent upon both, and in others, it's dependent only on the concentration of the alkyl halide. Now, in an SN1 mechanism, the mechanism is stepwise. What I mean by that is there's multiple steps. So the rate determining step, and this is the reason why the rate depends only on the concentration of the alkyl halide, involves the leaving group leaving. That's the rate determining step. The leaving group leaves with its electrons. So that bond, notice there's only one arrow there. That arrow is showing the bond breaking between the carbon and the halogen. And the reason this is the rate determining step, why it requires the most amount of energy, let's see if you can kind of think about it before I state the answer. You're going from a carbon that has a full octet to a carbon that only has 6 electrons around it. So it's not very happy. It's not stable at all. So that requires a lot of energy to get that to occur. Now, once that leaving group leaves, notice what we got there. We got a pretty good electrophile. So now in comes our nucleophile and makes a bond with that carbocation. So the end result is kind of the same. The nucleophile replaced the leaving group. It just went a different pathway than the SN2. Now I'm going to start by talking about SN2. It's kind of the easier one to grasp right now. And an SN2 proceeds through what is called a backside attack. And all that really refers to is where the nucleophile decides to make a bond to the carbon with the leaving group. So in this diagram here, a frontside attack would be the nucleophile comes in from the same direction as the leaving group. A backside attack is the nucleophile comes in from the opposite direction of the leaving group. Now, why do we care about what direction it comes in at? Okay, so why does this matter? It matters when the alkyl halide is chiral. If the alkyl halide is chiral, and let me be specific about this. The leaving group is on a chiral carbon. Okay, I want you to circle, highlight, star that. In fact, I'll do it as well. The leaving group is on a chiral carbon. Then the product results in what is called an inversion of configuration. So what do I mean by that? Let's take this alkyl halide here. So this alkyl halide's chiral. It's got four different groups around this carbon right here, a carbon with the leaving group. And we're going to react it with a nucleophile. We'll just use this SH minus, pretty great nucleophile. And that is going to come from the opposite direction of the leaving group. So there's our SN2 mechanism. And let me draw the transition state of this. So remember, transition state is something that looks a little bit like the reactant, looks a little bit like the product, but it's not really either one completely. So this dot, those dots there are demonstrating that the sulfur is making a bond with the carbon. At the same time, the bond between the carbon and the bromine is breaking. And then we got our other groups here. Now, once that bond forming and breaking is complete, notice this SH group is going in the opposite direction the leaving group was going in. If I do my R and S configuration for the reactant, this has the R stereochemistry, and for the product, it has the S stereochemistry. So this is why we care what direction the nucleophile attacks in. If the leaving group is on a chiral carbon, then that results in inversion in configuration. Now, if the leaving group is not on a chiral center, then we don't care about stereochemistry. But whenever the leaving group is on a chiral center, you always have to have stereochemistry in mind when it comes to these nucleophilic substitutions. Now, why does the backside attack occur? I kind of explained what happened. The nucleophile comes from the opposite direction of the leaving group, so not a front side attack. But why does it come from the backside? Well, there's a semi-okay answer, which works, and then there's a much better answer. The kind of okay answer is, let's imagine we got a nucleophile here with a lot of electron density. Do you think it wants to come from the same direction that that massive leaving group is with all of its electrons? No, it doesn't want to do that because of sterics. It's much less sterically hindered by coming from the back direction. Doesn't have to deal with that big leaving group and all of its electrons. Now, the better explanation is to use molecular orbital theory. So in a reaction involving a nucleophile and an electrophile, the electron density, according to molecular orbital theory, flows from the highest occupied molecular orbital. Remember, that's what the H and the O stand for. Highest occupied molecular orbital of the nucleophile to the lowest unoccupied molecular orbital of the electrophile. So a nucleophile wants to attack an electrophile where that electron density is the greatest. You have something that has electrons, or there's electrons in that highest occupied molecular orbital, and it wants to make a bond with that unoccupied molecular orbital. If a nucleophile tried to attack from the front, it actually would try to connect at what's called a node. No electron density can exist at the node. And so that would result in no bond being formed. Rather, the highest occupied molecular orbital of the nucleophile, has a really great opportunity to overlap with the LUMO of the electrophile by attacking from the backside.